This is a sample of a retrosynthetic analysis problem that you may encounter on Test 1 in Organic Chemistry Part 2. There will be an ether functionality, so you best review the Williamson ether synthesis. You also will have to employ Grignard or organolithium addition to aldehydes and ketones, and Grignard organolithium additions to epoxides. This problem will not go very well if you don't know what benzyl alcohol is. Let's quickly review. This is benzyl alcohol. This is not benzyl alcohol. This is phenol. You can't do what we need to do with phenol. And you're not allowed to start with phenol. After reviewing the Williamson ether synthesis, I hope you recall you need a nucleophile and an electrophile. You have two choices, this being the O- attached to this nucleophile, attacking a carbon with a leaving group here, which would be a terrible choice. You can't attack a tertiary carbon. So that leaves as your better choice this being the O- nucleophile, attacking a carbon with a leaving group here. This combination would do that. This creates a new retrosynthetic analysis. Where does that come from? Where does that come from? Let's do the easier one, the one on the right side. Alkyl bromides come from alcohols. Now the question is, how did benzyl alcohol gain a new carbon? Realizing that a Grignard or an organolithium reagent if it attacks an aldehyde will become a primary alcohol, that simplifies this problem to an aldehyde being attacked by an organolithium. Now the problem is, where do organolithiums come from? And where do aldehydes come from? Let's deal with the easier one again. Aldehydes come from alcohols. Methanol in this case. Circle it. It's on your list of allowed chemicals. Alcohols of 5 carbons or less. Organolithiums can only come from alkyl halides. Alkyl halides, such as this species, come directly from alcohols. Circle it. It's benzyl alcohol. You're allowed to start with it. There are several approaches to think of to make this species. If this carbon was a nucleophile, it could have attacked a carbonyl to create this O-. Let's explore that possibility. Organolithium meets the bill for a nucleophile. Ketone meets the bill for this species. Those two would give the above result. Where does this come from? Is the easier question. Where does this come from? A little more thought. Let's always deal with the easier one first. Alcohols are easily made into ketones. This alcohol has 4 carbons. This alcohol gets circled. Organolithiums only come from alkyl halides. Alkyl halides can easily come from alcohols. Sadly, the benzyl portion only takes you to here. I seem to recall a reaction where if that carbon off of the benzene is a nucleophile, I can attack something on 1 carbon and get an alcohol 1 carbon away. That is called nucleophilic attack on an epoxide. The nucleophile we already have the nucleophile. The epoxide would have 2 carbons in a triangle. We've already done the retrosynthesis of the organolithium by way of the benzyl bromide to the benzyl alcohol. We need to review that epoxides are made from alkenes. And alkenes are easily made from alcohols. Pesky box. Put a circle around it. That's a 2-carbon alcohol, thus concluding the retrosynthetic portion of this question. As you can see, I've copied all of the circled molecules from the end of the retrosynthetic analysis to the top of the page. Questions are, how do you make an alcohol into an alkyl bromide? The answer is PBr3. How do you convert an alkyl bromide into an organolithium? The answer is lithium metal. Solvents such as hexane. How do you convert a secondary alcohol into a ketone, the answer is PCC. Alternative answers could be potassium dichromate in aqueous sulfuric acid or chromium 6 oxide in aqueous sulfuric acid. No alternatives for the methanol becoming formaldehyde. PCC is the only one that would work in that case. How do you convert an alcohol into an alkene? The answer is acid catalyzed dehydration of the alcohol found in chapter 10, accomplished using H2SO4 in the presence of heat. Just for interest's sake, if you want to put a Greek letter on anything using computer programs, the font you want is the symbol font. How do we convert an alkene into an epoxide? There are several ways. A per acid is usually the fastest way. Monomagnesium perphthalic acid is a good one. Metachloroperbenzoic acid is another one. Peracetic acid is yet another. Or the two-step procedure of halohydrin formation using bromine in water, followed by sodium hydroxide, which creates an NGP situation, also creates epoxides. Keep in mind, we did a sulfur ylide preparation of epoxides from carbonyl compounds that you might want to review as well for the test. Okay, you don't, it's not might want to review, you should review. We have to convert this species into both this alcohol and this alcohol. This is the one with one more carbon. Step 1 will involve using the formaldehyde we created here, followed by HCl. To create this species down here, we have to get 2 new carbons. That is where step 1 is our epoxide, followed by, you guessed it, HCl. HCl in both reactions provides a proton for your alcohol. Note that I've gone from the alcohol to the organolithium here, which really takes us from this species to this species without showing the one in the middle. You can do this on the forward synthesis. Just show that you know it really reflects 2 steps. First step, PBr3. Second step, not HCl. Second step, lithium in hexane. Now the question is, how can I make this species down here with the organolithium into this that has the new bond right here? And the answer is step 1, the butanone, followed by step 2. Oh, there's no step 2. We want to keep the O-. Final question, how do we make this penultimate intermediate here into our target molecule? The answer is a Williamson ether synthesis. This is the nucleophile for the synthesis. This is the electrophile for the synthesis. Sadly, I have not shown the step that makes this electrophile. Happily, it comes from this alcohol here. What chemicals convert alcohol to bromine? We already have it on the page. This concludes our retrosynthetic analysis. Congratulations.